Okay, so in the last lecture, we discussed the Green's function method to solve differential equations. So the crux of this method is actually quite simple. Let me quickly recap what we did, and then we will apply this method to the scattering problem or the solution of the Schrodinger equation in general. Right? So we gave an example of a driven simple harmonic oscillator. So d square y dt square plus omega 0 y equals some f of t, right? So we looked upon this right-hand side as the stimulus, and the y, which is the amplitude, is the response to this stimulus. Right? So this is, in this case, it was a driving force. Okay. So the way we solved this problem was to look at this operator d square over dt square plus omega 0 square. And then we basically asked if the driving force was instead a delta function in time, what would the response be? So we wrote down an equation for the delta function driving force, which was, so let's call this operator some L. Okay, some linear operator L. So we wrote down L g t minus t prime equals delta t minus t prime. Okay. Sorry. Is it, seems to be not showing. Okay. Okay. So why t minus t prime? Well, because the delta function acts at one particular instant of time when t equals, let us say, 5 seconds or 10 seconds, and that is this t prime. Right? It's some particular time interval. And now the response on the left-hand side is also a function of t minus t. Okay. So now we solve this equation and solve this differential equation in terms of using Fourier transform techniques. Okay. So basically we plug the Fourier transformation of g of t minus t prime, which is over here. Yeah, on the top line here. And then using this Fourier transform, we were able to get a simple algebraic equation for the inverse Fourier transform, g tilde of omega, which is over here. And then we plug this g tilde back in the formula for the Fourier transform and evaluated g using some contour integration techniques, right? And once we found g, the solution was very easy. Once you find g, the solution is simply given by integral g of t minus t prime weighted by the actual driving force over the entire range, whatever this entire range is. Suppose if the force acts from minus infinity to infinity, this is minus infinity to infinity. If the force acts from 0 to infinity, the integration is from 0 to infinity, so on and so forth. Okay. So the integration limits depend on the problem at hand. So remember, I'm integrating over all such delta function impulses. So I'm integrating over t prime, and the right hand side is obviously a function of t, and this gives me the amplitude of the simple harmonic oscillator in response to the driving force f of t. Okay, so it's basically integrating the Green's function weighted by the driving force over the entire range of time. So one important thing to notice here, which is different in our Schrodinger equation picture, is that there is no y on the right hand side. You see, the driving force is independent of y. For example, if the driving force depends on how high the oscillator rises, then the right hand side would also be a function of y. So f of t times some y of t. Then of course, in this, we can still do this, but the integration, the right hand side would also involve a y of t prime. Okay, and that would make things a little more complicated, because that would not be a solution anymore. That would be an integral equation. I'll explain what this means in the context of the Schrodinger equation. But essentially, this is what we'll be doing for the problem at hand, which is scattering theory. So let's get back to scattering theory.
Sir?
Yes.
I had a question. So you said that this interval t minus t prime can be anything, right? But we essentially say that this is an impulse. So shouldn't there be some kind of bound on t minus t prime also? I mean, how can it be from minus infinity to infinity and we can call it an impulse?
Sorry, can you say that again? Shouldn't there be
Yeah.
what else?
So you said that this time can run from minus infinity to infinity, right?
Hmm.
But we are saying that this is an impulse.
Hmm.
So shouldn't it be like for a small amount of time only?
No. So there is two different things here. The driving force acts for whatever time you decide. So f of t is what you push the oscillator with, right? So let us say that there is a block, right, of mass m, and I'm pushing it with some force f of t. Okay. Now, basically, what I'm claiming is that now, what does classical mechanics tell you? Classical mechanics tells you what's the acceleration of this mass m in response to this f of t, right? So you solve this differential equation and integrate this differentially, integrate this or whatever it is, do whatever you like to do, and then solve this differential equation to get x of t. That is your goal, right? To find the position as a function of time. Agreed? Now, instead, what I'm claiming is that instead of looking at this motion of this object as a continuous motion, piece up this f of t into delta function impulses, which means that the guy who is pushing it, imagine that he's pushing it for 1 second like this, and the block moves over here. And then 1 more second, the block moves over here. 1 more second, the block moves over here. And keep doing this. Okay. In other words, your f of t can be anything. So if I graph f of t as a function of time, f of t, for example, you may push it with a lot of enthusiasm in the beginning, and then you can sort of taper off and you feel tired. Okay. But regardless of the form of f of t, what I'm basically claiming is that instead of looking at this time as a continuous variable, well, time is still a continuous variable, instead of looking at this f of t as a function of time for all intervals of time, look at it for a series of impulses. So let us say that the force acts from 0 to 100 seconds. Okay, at 100 seconds, you stop. Okay. Now, between the 0 and 100 seconds, I will look at, for example, 1 second impulses. So here, here, here. Okay. So basically, I'm piecing up this force into 100 delta function impulses. Now, if I join all these 100 delta function impulses, of course, I should be getting back my usual force. But your question is, how can you just have delta function impulses? Shouldn't you also have some weight for the delta function impulses, right? So, for example, if I simply look at it as a delta function impulse, what is the, this delta function impulse here simply tells me that there is a force of unit amplitude at, let us say this is 5 seconds, right? But the actual force is not unit amplitude, it is some other magnitude. Well, that is taken care of in the actual solution where I weight it with the actual force at that particular time. So you see, what does this integration represent? This integration represents the following. G of t minus t prime is the response of the system corresponding to a delta function impulse at time t equal to t prime. So which means that at t equal to t prime, if there is a delta function impulse, the object moves, let us say, vertically 1 centimeter. Okay. But I don't want it for a delta function impulse, because at this particular time, the actual driving force is whatever value it is. Let us say that it is 5 newtons. So I want the response for a 5 Newton driving force. So basically, I'm weighting this delta function response with the actual force. Okay, so this will be the actual response at time t equal to t prime. Now I'm integrating over all possible t primes, which means in this particular example, I'm integrating from 0 seconds to 100 seconds. Okay, considering, for example, 100 delta function impulses. So at each point, there is a delta function driving force for which I know the response G. And at each point, I know the actual response of the system, because it is just G times the driving force f of t prime. And I simply integrate from 0 to 100 to give me the total response as a function of time. Does this make sense?
Yes. Okay, sir. Got it.
Any other questions or comments? Okay. is this. So let's go back to scattering, in particular the Schrodinger equation. So there is some scattering potential B, which I take to be rotationally invariant. So it is only a function of the absolute distance. Okay, V has no information about the angles. That is an assumption that I'm constantly making. Now, let me just write down the Schrodinger equation. So this is minus h bar square over 2m del square plus V of r acting on psi, of course, is a function of distance and angles. Okay. Now let me recast this equation into an equation like this, wherein I have some differential operator acting on some response of the system equals some driving force. So what is the driving force here? Well, it's not a force, it's a potential. So whatever is causing dynamics is the potential V of r. So the equivalent of the f of t is basically V of r here. Okay. So if I rearrange this equation, for example, I will get h bar square over 2m del square plus e psi of r equals V of r psi of r. Okay. So this is the response. The wave function is basically the response. And this is the equivalent of the driving force or driving potential, which is a bad term, but whatever it is. It is the equivalent of the driving potential. So as you can see, the difference between the Schrodinger equation and a driven harmonic oscillator is that the driven harmonic oscillator on the right-hand side does not have y of t. Okay. But here, the right-hand side, the driving force also has a psi of r, the response, which means if I want to calculate the response by using the Green's function technique, I actually need to figure out what the response is. So if I solve this differential equation, again, let me do the exact same thing. So let me take this as a linear operator L. So basically what I'm going to do is solve the response of the system with respect to a delta function driving force. So which means I'm going to solve G of r prime equals delta cube r minus r prime, let us say. Okay. Now, based on translation invariance, because translation invariance means that if I do r to r plus a, the right hand side is invariant. So the left hand side should also be invariant. So my Green's function should actually be a function of the actual difference, just like the right hand side. Okay. So assume that I know what this Green's function is. Now, how do I construct the solution just like I did for this driven harmonic oscillator case? Well, I'll have to calculate the response for a delta function impulse. I have to integrate that, weight that with the actual driving force at every single point of space r. Here it is a function of space r prime and not t prime. And then I have to integrate over all space d cubed r prime, right? So that is the exact analog of this equation, except that my driving force also has a psi. So if I want to write down the solution, psi of r would be phi of r plus, I'll tell you what this phi of r is in a second, d cubed r prime g of r minus r prime, whatever the Green's function is, times the driving potential, which is V of r psi of r. So V of r prime psi of r. Okay. Now, what is this phi of r? So remember that in the initial discussion 2 days ago, when I introduced this phi of r. I'm sure I did it somewhere. So this is the phi here, phi vector here. What is the phi vector here? The phi vector is the solution of the free Hamiltonian H0. In this case, then what is the solution of the free Hamiltonian? The free Hamiltonian is, of course, H0 is, of course, minus h bar square over 2m del square, right? So phi is anything that satisfies the eigenvalue equation of the free Hamiltonian. So H0 phi equals E phi, which tells me phi is just your usual e to the I k dot r, right? So psi of r equals e to the I k dot r plus integral d cube r prime d of r prime psi of r prime. Okay. So this is the formal analog of the solution of the driven harmonic oscillator. The only difference is that I've added the solution of the free free Schrodinger equation, which is something I can always do. Okay. So you can actually check by acting this on the actual Schrodinger equation that the Schrodinger equation, this is a solution. But this is not a solution in the traditional term, because what is a solution? A solution is something you write an unknown quantity in terms of the known quantities. Okay, k dot r is fine, but on the right hand side, I know what the Green's function is because I've calculated the Green's function. I know what the potential is because the potential is given to me. But I also need psi of r prime, which means to understand the response over all space, I need to understand the response at every particular instant of time, which also involves the same wave function. So to calculate the wave function, I need the wave function. So on the looks of it, it looks like a silly way to solve a problem, right? Because to understand the solution, I actually need the solution. But this equation is of immense help, and I will explain how to view this equation and how to understand and extract information from this equation in the coming lectures. But for now, recognize that this is the formal solution of the Schrodinger equation. This is not a solution in the traditional sense. It is called an integral equation. Mathematically, this is called an integral equation because it relates psi to psi itself via an integration. Okay. So for the rest of today's lectures, we will be concerned mostly with the Green's function for this problem. Okay. So let us set up the Green's function for this problem, and then we will use the Green's function to reinterpret this equation, and then we will go on to see what the scattering solution looks like. So to understand the Green's function, let's go back to the Schrodinger equation. Del square plus V of R. So let me use the form that I just wrote down, which is h bar square over 2m del square plus E psi of R equals V of R psi of R. Okay. So Green's function is a solution psi where the response psi of R is the response to a delta function driving potential. So the Green's function is defined as h bar square over 2m del square plus E acting on G R minus R prime. Why R minus R prime? Again, it's because we demand the solution to be translation invariant equals delta Q R minus R prime. Okay. So we can clean up this equation a little bit by multiplying by 2m over h bar square. So if I do that, this equation becomes equals 2m over h bar square delta cube r minus r prime, where k square is the usual 2me over h bar square. Okay. So this is the equation I need to solve. This is the equation that will tell me what the Green's function for the problem is. Is there any questions about this equation? Any questions or any comments up till now? Okay. So to avoid writing r minus r prime all the time, let me call this as some x. Okay. So notice that del square is a function of only r, not r prime. Okay. So del square has things like ddr, d square dr square, not r prime square. So this is important to recognize. Okay. So let me write down the Fourier transform and inverse Fourier transform without much ado. So G of Q, the inverse Fourier transform, the conjugate variable, of course, for position is momentum. The momentum I'm calling Q. This is, I integrate over okay. So this is the inverse Fourier transform, and of course the Fourier transform has a plus, excuse me, has a plus IQ dot x. Okay. So I will write everything in terms of the Fourier transform. So remember that delta cube also has a representation plus IQ dot x. Okay. So let me call this equation 1, equation 2, and equation 3. And let me call this equation A. So substitute 2 and 3 in A. In other words, write all the G's and the delta functions in terms of their transforms. If I do that, I have del square plus k square G of x vector, which is integral d cube q over 2 pi q e to the I q dot x g tilde q. So sorry about my handwriting. This is a tilde, not a vector, right? So q is a vector. The right hand side, of course, is 2m over h bar square integral d cube q over 2 pi e to the I q dot x. So now we do the usual trick by claiming that on the left hand side, the integration is over the variable q, and the del square is differentiation with respect to the variable r in x, right? So I can, with impunity, take the del square plus k square inside the integration, because integration with respect to one variable and differentiation with respect to a different variable, the order can be interchanged. So if I do that, e cube q over 2 pi cube, notice that del square plus k square only acts on the e to the I q dot x part, because g of q vector is only a function of the momentum, the conjugate variable, and not position. So del square has nothing to do with g tilde. So del square plus k square acting on e to the I q dot x g tilde q vector equals the right hand side as such. Okay. So del square plus k square e to the I q dot x is basically del square plus k square acting on e to the I q dot r minus r prime, right? So the del square doesn't care much about the q dot r prime, but it looks at the q dot r, and for every, if you look at it in terms of Cartesian coordinates, del square is basically d square dx square plus d square dy square plus d square dz square. So each one of these guys pulls out a factor of IQ whole square. So this is simply, excuse me, IQ square plus k square acting on e to the I q dot x, where q square is, of course, q is basically modulus of the absolute modulus of q vector. Okay. So if I clean this up, I get minus q square plus k square e to the I q dot x. So substitute this in the integral, so in the equation above. So I get the left hand side d cube q over 2 pi quantity cubed minus q square plus k square e to the I q dot x g tilde of q, and this is equal to, okay. So if this has to be true, the integrand on both sides have to be equal. That is the only way, because I can write this integration as d cube q over 2 pi cube. I can also take the e to the, excuse me, e to the I q dot x common outside, and I will have minus q square plus k square. Sorry, there is a 2m over h bar square, which I missed. G tilde q minus equals 0, right? So e to the iq dot x is not 0, it's an oscillatory term, which means the only way this integration can be equal to 0 for any q and for any x is if the integrand identically vanishes. This tells me that I can get g tilde by a simple algebraic equation. So minus q square plus k square g tilde has to be equal to 2m over h bar square. Okay. So which means g tilde of q can be written as minus 2m over h bar square 1 over q square minus k square. I pulled out a negative sign and I wrote it in terms of q square minus k square instead of k square minus q square. So this is the Green's function in momentum space for this problem. So the next job is, of course, to figure out the Green's function in position space. So the formula is simple enough. G tilde of x is, of course, 1 over 2 pi quantity cubed integral d cube q e to the I q dot x g tilde of q vector. Okay. So if I use this, my Green's function in position space is minus 2m over h bar square 1 over 2 pi quantity cube integral d cube q e to the I q dot x divided by q square minus q square. Okay, is that fine? Any questions or comments about this? Okay, so if there's no questions, let's proceed. Now, we will have to evaluate this using contour integration because I'm going to put in a I epsilon prescription. But before I do the I epsilon prescription, let me integrate over the angles. Okay. So remember that the integrand is rotationally invariant. So this is rotationally invariant. What does this mean? It means that if I rotate this guy, everything here is a scalar. Q dot x, dot product of two vectors is a scalar. Q square is a scalar because it's Q dot Q. So everything here is a scalar. It doesn't depend on the angles at all. So it is actually invariant under rotations because scalars don't change. Scalars are numbers, which means I'm free to position my axis in any way I want. I'll position my axis such that Q is along the Z direction. X is along the QZ direction, which means Q dot X can be written as Q X cosine theta. Okay, so this can always be done because there is no explicit dependence on angles in the integrand. So remember that there is no phi anywhere. So integration d phi is simply going to give me a factor of 2 pi. So if I account for the factor of 2 pi, 1 over 2 pi cube, and there is going to be a factor of 2 pi, and then there's going to be a q square dq from 0 to infinity integration. Okay, and then there's going to be a q square minus k square here, and then there's going to be integration with respect to cosine theta, right? So I can write this integration as minus 1 to 1 e to the I q x y dy, where I have called y as cosine theta. Okay. Which means, remember that the usual integration is integral d theta sine theta, which can be written as minus dy. So if I use that, I get this particular form. So what is the integration over the cosine theta variable? This integration, excuse me, this integration, let's call this k. K is basically e to the I qx y divided by I qx between plus 1 and minus 1. So this is, if I put y equals plus 1, I get I qx. I don't have any y in the denominator. Minus e to the minus I qx divided by I qx. It is tempting to write this as sine qx, and of course you can do it. But for our purposes, since I'm going to do contour integration, I'm going to keep it in the e to the iqx form for now. So let me write down the integration again. So g of x is given by minus 2m over h bar square 1 over 4 pi square, because there is 3 factors of 2 pi, 1 factor of 2 pi. So 1 factor of 2 pi goes away. 2 pi whole square is 4 pi square. And there is a factor of ix in the denominator that can be pulled out because the integration is only over q. So what remains is q square dq e to the iqx minus e to the minus iqx over q. So what is this x? Remember, x is the absolute modulus of x. This is equal to the absolute modulus of r minus r prime. Okay. So the Green's function, which we surmised should be a function of the vector r minus r prime, is actually only a function of the absolute value of the vector r minus r prime. Okay, it's not a function of x vector. It is only a function of the absolute value of this vector r minus r prime. Okay. So let us look at this integration. Let's call this k prime. K prime is given by 1 factor of q cancels. So I'll have dq q. Oh, sorry, I forgot the factor of q square minus k square here, right? So let me write this properly. Q times q square minus k square. Sorry about that. Q e to the iqx minus e to the minus iqx divided by q square minus k square. This is my integration. Is everyone with me so far? Are there any questions?
Yes, sir.
Okay. So instead of jumping and writing in terms of sign, since I want to do contour integrations, I like the e to the iqx form. So let me keep this in the e to the iqx form. So first I will split this into 2 integrations. So I'll write this as 0 to infinity dq q e to the iqx divided by q square minus k square, and minus 0 to infinity dq q e, excuse me, q e to the minus iqx q square minus k square. Okay. Now look at this guy. In this, I will do a change of variables. I will say q goes to minus q. What happens if q goes to minus q here? I'll get 0 to infinity. dq will become minus dq. Q on top will become minus q. Okay. Oh, sorry. The integration will also change. Right? 0 will remain 0, but this will become minus infinity because q goes to minus q. E to the iqx will become e to the plus iqx, and q square minus k square, of course, will not change because minus q whole square is just q square. So what is this equal to? Two of these guys, there's two negative signs. So this is basically 0 to minus infinity dq q e to the I qx over q square minus k square. Okay, I'm just doing a change of variables, which I can always do. But notice that there is a minus sign in front of this integration. So I can use this minus sign to flip the order of integration from minus infinity to 0. So if I do this, I can write these two integrations as the first one I will keep as such, dq q e to the I qx q square minus k square. The second one becomes plus minus infinity to 0 dq q e to the I qx q square minus k square. And now if you stare at these two integrands, you will see that they are the exact same things. So I can simply combine these two integrations into one integration from minus infinity to plus infinity. Okay. So this is exactly the same as what I have here as k prime, except that by a change of variables in the second term, I was able to bring the second term to look exactly like the first term. So I was able to combine these two integrations into one integration. And now I've integrated over all the variables. I've done the massaging of the integrand to bring it into a manageable form. So the only thing that remains is basically solve this integration. Solve this integration, I will use the I epsilon prescription. Solve using contour integration and the I epsilon prescription. What is the I epsilon prescription? Well, this, which is basically a decent, respectable function of a real variable q, is now going to become an obscene variable, which is imaginary also. So I'm going to write this as minus infinity to infinity dq q e to the I qx divided by q square minus k square minus I epsilon. I'm going to deliberately put in a factor of I epsilon so that I can do the integration over an imaginary q axis also. So now the real variable q is now becoming an imaginary variable q. So I can, this integration over minus infinity to plus infinity can be thought of as an integration over the entire complex plane. Of course, I have to take the limit epsilon going to 0 at the end. So remember, I'll write a note for myself. Take the limit epsilon going to 0 at the end, because after all, q is a real variable. Okay, it's a conjugate variable to x, which is r minus r prime, which is a manifestly real variable. So just because I make things complex doesn't mean that they become automatically complex. This is just a trick. The second point that you have to remember is that I have a minus I epsilon here and not a plus I epsilon. I can also put in a plus I epsilon, right? Nobody can stop me at this stage. But as I will remark later, using the prescription plus I epsilon for this problem will give you unphysical results in terms of the problem at hand, which is scattering problem. So I'll explain what this means when we write down the solution. So now I will write this as an integration. So first let me piece up this denominator as q minus k plus I epsilon q plus k plus I epsilon. Okay. Why is this valid? So if you evaluate this guy, you will get, this is a plus b times a minus b. So this is a square minus b square, which is q square minus k square minus epsilon square plus 2I epsilon k, which can be thought of as q square minus k square minus I epsilon, because I'll absorb the 2k factor in the epsilon itself. If epsilon is small enough, 2 epsilon k can be thought of as epsilon. And since epsilon is very small, I'll neglect epsilon square in comparison to epsilon. So I can factor this denominator q square minus k square minus I epsilon in this fashion. So now I have to use contour integration to solve this sucker. So if I do that, Okay, so this is the complex plane. So this is the imaginary q, this is the real q axis. Now, first let me look at the poles. Of course, this integrand has two simple poles, one at q equals k plus I epsilon and one at q equals minus of k plus I epsilon. So where is q equals k plus I epsilon pole? Well, k plus I epsilon plus I epsilon means it is in the positive imaginary axis, so it's over here. And plus k means the real part of q is also positive, so the pole k plus I epsilon is right over there. So this is the pole k plus I epsilon. The other pole is q equals minus k minus I epsilon. So minus k means it's on the left hand side because the real part of q is negative. And minus I epsilon means it is in the bottom of this graph because the imaginary part of q is also negative in this case. So it's symmetric about this origin. So the other guy is right over here. So this is the other pole minus k minus I epsilon. Okay. So now I have to choose a contour. So what is the contour that I will choose? Well, I want to cover the entire complex plane as much as possible. So of course I can choose an entire circle or cover just the top half or cover just the bottom half and pick up one or both of these poles. And if I pick up one of these poles, I will simply use the Cauchy theorem and claim that I'm dealing with an analytic function except one small point where it has a singularity. It's a simple pole. So the actual answer is basically 2 pi I times the residue at that particular point. So the question is, what is the path I have to take for the integration? The path I have to take for the integration is, of course, on the upper side. So this is the path I have to take. Okay. Where the radius of the circle, I'll call this radius of this semicircle, equals r, which is a very, very large value. So I'll take r to infinity. Now, why should I close it at the top half and not the bottom half? So can anybody answer? Why can't I close the integration from the bottom half? If I close it from the bottom half, what happens is, remember that I'm making q imaginary. So let's call q equals q real plus iq imaginary, right? So let us look at the contribution to this integrand from very, very large imaginary portions, where the actual value along the path of integration is the radius of the semicircle. So the imaginary part of q is the radius of the semicircle. So this is at large imaginary values, this becomes qr plus I times capital R. So what is the integrand? The integrand has a factor of e to the I q x, which can be written as I q real plus I r x, which is e to the I q real x e to the minus x r. So if I take the radius of this semicircle to infinity and if I close it on the top half, I get e to the minus xr, which means all the contributions from all these imaginary, infinite contribution of the imaginary axis basically goes down to 0 because it is exponentially suppressed. If I close it at the bottom, I will actually get e to the plus xr. So the contribution to the integrand from very large imaginary values is actually infinitely large, which is something I don't want because I know that my integration is over a real variable. So I should ensure that all the contributions from infinite amounts of the the imaginary part of the complex plane should actually die down. Okay, so that's why in this problem I should close it on the top half and not the bottom half. There could be problems in which I can also close it in the bottom half, but this is not one such. So basically, when all is said and done, my integration simply becomes 2 pi I times, if I close it the top half, I only pick up the pole at k plus I epsilon. The k minus I epsilon, minus k minus I epsilon is outside my region of integration. So this basically becomes 2 pi I times the residue at q equals k plus I epsilon of this function, this entire function, whatever this is, q times e to the iqx times q minus k plus I epsilon times q plus k plus I epsilon. How do I take the residue with a simple pole? I simply multiply, remember that residue at x is equal to x0 of f of x, or let me use z. Residue at z equals z0 of f of z, which is where z0 is a simple pole, is basically z limit z goes to z0, z minus z0 times f of z. Right? So that is the formula for the residue for a simple pole. So if I use this prescription, this is basically 2 pi I times limit q goes to k plus I epsilon. Z minus z0 in this case is q minus k plus I epsilon times q e to the iqx q plus k plus I epsilon. So as you can see, of course, this is always true in simple poles, that this factor cancels this factor. So the answer to this integration is basically 2 pi I. I should simply, wherever I see q, I should just substitute this by the value of q at the pole, which is k plus I epsilon. Divided by, the denominator has q plus k plus I epsilon. So there is two factors of k plus I epsilon. Okay. So that is my q integration. So let me put everything together now. If I put everything together, my g of x becomes minus 2m over h bar square 1 over 4 pi square. What else did I have? 1 over ix 1 over ix times this whole thing times 2 pi I times, now I will take the limit epsilon going to 0, limit epsilon going to 0 of k plus I epsilon e to the I. So let me piece this up. E to the ikx e to the minus epsilon x divided by 2 times k plus I epsilon. And of course, epsilon going to 0 limit of this function exists. So this is nothing but k e to the ikx over 2k, right? Which is basically e to the ikx. So plug in everything and you get the Green's function for this problem as minus 2m over h bar square 1 over 4 pi square 1 over ix 2 pi I e to the ikx. So one factor of I cancels by 2, sorry. Because there's a factor of 2 here which you cannot miss. So one factor of 2 cancels, one factor of pi cancels. So putting everything together, I have minus 2m over h bar square 1 over 4 pi e to the ikx over x. Okay. Or in other words, the Green's function for the operator del square plus k square can be written as g of r minus r prime is equal to minus 2m over h bar square e to the ik r minus r prime modulus divided by r minus r prime absolute modulus. Okay. So this is the Green's function for the so-called Helmholtz equation, del square plus k square equals 5x. So now that we have derived the Green's function, we will use this Green's function to write down the solution for the problem, and then we will interpret and figure out how to understand the scattering solution. Okay. So we will stop at this point, and then we will take this up further when we talk about the actual solution to the scattering problem.